Let's talk about enthalpy of neutralization. This is the heat change that occurs when an acid is neutralized by a base. Heat change that occurs is neutralized by a base. Experiment. The procedure: wrap a cleaner 250 millimeter beaker with tissue paper. And secure the tissue paper with a rubber band. Transfer accurately 50 cubic centimeters of 2 molar HCl into the beaker and note its temperature as T1. Using a clean, dry measuring cylinder, measure accurately 50 cubic centimeters of 2 molar sodium hydroxide. Note it as T2. Add the 50 cubic centimeters of 2 molar HCl carefully. Stir the content in the beaker while adding. Note the final temperature as T4. Add 50 cubic centimeters of 2 molar HCl and stir the content. Then after that, note the temperature and record as T4. Experimental results. Temperature of HCl T1 is equals to 22.5 degrees Celsius. Temperature of sodium hydroxide T2 22.5 degrees Celsius. Then T3 is the average temperature, that is T1 plus T2 over 2, that will give us 22.5 degrees Celsius. then T for the final temperature, which is the highest, and that is 35.5 degrees Celsius. So we want to use this result to calculate the heat change. Delta H is what we want to calculate, and the heat change is mass times heat capacity delta T. So mass is calculated as follows. That is simply adding the two volumes to get 100 cubic centimeters, and the mass of the solution will therefore be assumed to be the same as density of water, so that gives a mass of 100 grams. Delta H is now equals to 0.1 kilogram by 4.2 kilojoule divided by kilogram times Kelvin times the difference in temperature, that is 35.5 minus the average, which is 22.5. So that is equals to 0.1 kilogram times 4.2 kilojoule times 13 Kelvin all over kilogram times Kelvin. That will cancel out, so we remain with 5.46 kilojoule. How do we now calculate molar heat of neutralization? First of all, we'll calculate the moles of the solution, starting with moles of HCl, that is 2 times 50 over 1000, giving 0.1 mole. Then moles of sodium hydroxide is equals to, again, 2 by 50, giving us 0.1 mole. So mole ratio is 1 to 1. Now, if 0.1 mole can give out 5.46 kilojoule, what will 1 mole give? So that is 1 times 5.46 over 0.1 kilojoule per mole, and that will give, if you divide well, get 54.6 kilojoule per mole. Heat is released during the reaction, and therefore molar heat of neutralization, heat is released, and therefore molar heat of neutralization is a negative 54.6 kilojoule per mole. Let's look at the thermochemical equation. The thermochemical equation will be as follows. Hydrogen ions from the acid reacting with the hydroxyl ions from the base to form water. Remember, this is neutralization. Delta H is negative 54.6 kilojoule per mole. Illustration in the energy level diagram. So let us have the energy level diagram. So this is y-axis, x-axis. We have reaction progress or reaction path. Then this is enthalpy in kilojoule. The reaction is exothermic, so we have the reactants, then products. There is that aspect of activation energy. Then our delta H is equals to negative 54.6 kilojoule per mole. So that is water as the product, and we have the reactants. So that is the energy level diagram. A molar heat of neutralization is the enthalpy change when 1 mole of hydrogen ions react with 1 mole of hydroxyl ions to form 1 mole of water. So it is 1 mole of hydrogen ions reacting with 1 mole of hydroxyl ion to form 1 mole of water. That is what we call the energy change involved during that is what we call molar heat of neutralization. Strong acids and strong alkalis are completely ionized in water. That is, strong acids and strong bases, or simply alkalis, are completely ionized in water. So the only reaction that takes place when they are mixed is the ionic equation, which involve a water formation. This explains why the standard enthalpy of neutralization between strong acids and strong bases is approximately negative 57 kilojoule per mole. The enthalpy of neutralization between weak acids and weak bases is lower. The one between weak acids and weak bases is lower. A reason being that some of the heat produced is used in ionization of the weak acids and bases. Apart from the fact that they are not fully ionized, and so the concentration of the hydroxyl ion and hydrogen ions in them is also low. They don't have many of those ions.